chapter 17, slides 8 through 12. Okay, we're going to wrap up the effects of aromaticity by talking a little bit about NMR and some other things that relate to aromatic compounds. So back when we did NMR analysis and we were looking at where certain protons came out on the chemical shift scale and ppm scale, what you'll notice is that we talked about it, but we didn't really talk about it. If you go back and look, you'll see that aromatic protons, meaning protons off of an aromatic ring, they tend to show up around 6.5 and 8.5 ppm. And that's kind of interesting, right? Because you think to yourself, well, most of the reasons why hydrogens appear so far downfield is due to deshielding effects. And deshielding effects tend to be because you have electron withdrawing groups nearby, electronegative atoms nearby, pulling electron cloud density away from that hydrogen. So you look at an aromatic ring and say, well, it's just a bunch of carbons and hydrogens. There's nothing particularly electronegative about it. But there are lots of stuff, there's lots of stuff going on in an NMR that is far oversimplified by just talking about electronegative atoms. Some of that has to do with the effects of the magnet. So in benzene in particular, since we're talking about benzene the most, the ring protons, right? The ring protons on the outside experience deshielding. That's why you see it so downfield, around 7 ppm, because the induced magnetic field has the same direction outside the ring as the external field, BO. So when you have this deshielding effect, these hydrogens on the outside have this purple, right? You can see the purple, that's the external field. And the external field and the induced magnetic field, that's the purple, and the external field in red, they're in the same direction. Okay, and that's what gives us the deshielding effect, which is why we see them so far downfield, 7.3 ppm. Now, you could argue that if your hydrogen, which it's not on a benzene ring, were inside the ring, which looks really bad, right, from a spatial electron bond perspective, but if it were inside the ring and it was with the yellow induced magnetic field of the resonance, it would be opposed to the external BO. And you would expect a shielded effect and see the hydrogens inside the ring way upfield. Well, we know that in benzene, these hydrogens exist outside the ring, and so that's why we see 7.3. But what's really kind of cool about this, to prove the point, is that in contrast, any proton inside an aromatic ring, and you might think, well, how could that be? Well, if the ring is big enough, like the one shown below, there are hydrogens that protrude inward, right? And so these inner protons are shielded because of the induced internal resonance field, which opposes the external field, BO, and we actually see the internal hydrogens of this system at -3 ppm, way upfield. And the outer ones of the aniline are downfield in the normal range, in the aromatic proton range. So this is kind of a cool example that protons within the aromatic system are shielded and protons outside the aromatic system are deshielded. And that's why we see the difference in their chemical shifts. Okay, another thing to recognize is that we now have enough information to go back to that example I gave you in the redox NADH example from back in the alcohol chapter. Remember when we were looking at the NADH molecule and we reduced this whole big green part, because that wasn't really the reactive center, to this R. We just called this R, okay? And then what was really happening was that the nitrogen of this ring system was dumping its electrons in, pushing these electrons over, and we saw an H minus as a leaving group. And we were like, what? And I told you, just hang in there. It'll all become clear. Like, what's the driving force for an H minus to get knocked off? H minus isn't a good leaving group, right? So what we know now is that when this nitrogen pushes its electrons in and pushes the pi bond over and kicks the hydrogen out, what started off as a non-aromatic ring system, after it kicks off the H minus, take a look at it, guys. It's now aromatic. It's a ring, fully conjugated. It wasn't fully conjugated because that carbon was sp3, right? So that was the blocker. It was a ring, but it wasn't a fully conjugated sp2 ring. It had an sp3 carbon blocker there stopping full conjugation around the ring. But when it pushes its electrons through and then kicks off the H minus to act as the reducing agent, the driving force for this is the fact that it forms a much more stable aromatic compound. NAD plus is stable because it's aromatic. Very cool. Now you can rationalize why H minus in this particular case is actually allowed to be kicked off as a leaving group. There is a thermodynamic, right? A stable product benefit for this to happen. Now, a little bit more about other materials out there. Some of you might have seen or heard about Buckyballs over the last decade or more. As early as the mid-1980s, there were only two really ways of seeing carbon that we knew of, right? Diamond, which if you look, is our chair. Look at those cyclohexane chairs, all just bonded to one another. You can see chair, 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 right? So it's interlocking chair conformations, while graphite is flat sheets of interlocking benzene rings. So, benzene ring interlocked with a benzene ring, and they're all sharing the double bonds. It's just interlocking benzene rings. So that's diamond and graphite. Okay, well, Harold Kroto and Robert Curl and Richard Smalley shared the Nobel Prize in 1996 for discovering a different type of carbon infrastructure. And they were trying to replicate carbon-rich stars using laser-induced evaporation of metals. And they reliably formed a compound that they saw had a molecular formula of C60. And they theorized that this C60 compound comprised of 5 and 6 alternating membered rings. Okay, so 20 hexagons and 12 pentagons. And they named it Buckminster Fullerene after the American architect Buckminster Fuller, who used to make buildings with geodesic domes. So these are now called Buckyballs for short. They only show one carbon-13 peak, meaning every carbon on the molecule is equivalent, and they're all sp2 hybridized atoms. And I've got a picture here of what the structure of a buckyball must look like. So given what we just learned about aromaticity, is a buckyball aromatic? Well, the answer would be no. Why? Because every one of those p orbitals, because of the ball shape, kinks the whole system out of plane so that those orbitals, those p orbitals, don't fully overlap with one another and thus aren't fully conjugated. Now, carbon nanotubes are also related systems, and since 1990, carbon nanotubes have found an array of different uses. They can be prepared under the conditions which ions are trapped inside, right? And when ions are trapped inside, then they can be superconductors at low temperatures. So you can see here, you can prepare a graphene sheet, and these graphene sheets can be rolled into carbon nanotubes. And again, the ions can be trapped on the inside, held by the p orbitals. And tubular fullerenes have also been prepared, and these are called nanotubes, and they are thought of as rolled sheets of graphite capped on either end. So that's what you can see here on either end of the nanotube is a cap. It's not open like a regular tube. So nanotubes are spun into fibers, and they tend to be stronger and lighter than steel, which is kind of amazing given that you're only using carbon and hydrogen. And they also can be made to carry electrical currents more efficiently than metals, again, due to the nature of the ions that it can be interwoven with.